Okay, in the today's session, we'll see thin cylindrical cells, right? So in the all previous sessions up to session 10, so we have understood the concept of stress, strains, different types of stresses, strains, and also we have solved around 20 to 25 problems on the stresses and strains. And in that we have studied the stress strain relations and how the stress strain curve varies for ductile material and a brittle material, and also we have seen the temperature stresses and strains. But in today's class we are studying thin cylindrical cells. So in this thin cylindrical cells I'm going to cover the topics like thin cylindrical cell, that is introduction part, and assumptions made in the analysis of thin cylindrical cells. Then next, failure of thin cylindrical cells. So let us start with the introduction. Thin cylindrical and spherical cells are used mainly for storage of gas, petrol, liquid, chemicals, and grains and so on, subjected to internal or external pressures. The name thin says the thin is pertaining to the thickness of the cylindrical shell. So where you are going to store the petrol, liquid like water, whatever it may be, in the liquid form if you are storing, so that is called as a cylinder. We call it as a cylinder. Cylinder means it is a hollow box or hollow shell where you are storing the liquid, petrol, chemicals, or even the food grains you can store there, right? So ನೀವು ರಸ್ತೆಯಲ್ಲಿ ಹೋಗ್ಬೇಕಾದಂಗೆ ನೋಡಿರ್ತೀರಿ, ಪೆಟ್ರೋಲ್ ತೊಗೊಂಡು ಟ್ಯಾಂಕ್ಗಳು ಹೋಗ್ತಾವ, ಪೆಟ್ರೋಲ್ ಲಾರಿ ಹಿಂದೆ ಪೆಟ್ರೋಲ್ ಟ್ಯಾಂಕ್ ಇರುತ್ತಲ್ಲ, ದಟ್ ಟ್ಯಾಂಕ್ ವಿ ಕ್ಯಾನ್ ಕಾಲ್ ಇಟ್ ಆಸ್ ಎ cylindrical shell there. So the walls of that cell is made up of a thin sheet of material, that thin sheet of material, right? So and when you store the liquid gas under a pressure, so under a pressure, then definitely there induces certain stresses. So certain stresses, what are those certain stresses? We'll see it in the further slides. So when you store a liquid under pressure in a cylinder, so it undergoes internal pressure as well as external pressures. But in our syllabus now we'll see how this internal pressure this internal pressure affects on the walls of the container. Walls of the container means walls of the cylindrical shell. And now their d by t ratio, d means diameter of the cylinder, t means thickness of the cylinder. When you take ratios of diameter and thickness, that is the ratio of diameter to wall thickness is large. The ratio of diameter to thickness is large. If the ratio of diameter to thickness is large, then such a shell we call it as thin cylindrical shell. That is d by t is greater than 20. If the ratio of thickness and diameter is greater than 20, then we call that as the thin cylindrical cell. If it is less than 20, then we call it as a thick cylindrical cell. But for your syllabus, you are having only the thin cylindrical cell, so that you can remember, if you want to call that as a thin cylindrical cell, then the ratio of the diameter to thickness is more than 20, right? Because in comparison to diameter, thickness is very small. In comparison to diameter, thickness is very small, so the ratio is greater than 20 here. So the variation of stresses along the thickness is taken negligible. So wherever a vessel is subjected to internal pressure due to a steam, compressed air, or etc., means anything like liquids or whatever it may be, so which you are storing under pressure, right? Its walls are subject to the tensile stresses. Then the walls of that container, walls of the cylinders are subjected to the tensile stresses. So to understand or to analyze the cylindrical cell, how the stresses are induced in the cylindrical cells, so we need to make some assumptions. sir, right? We need to make some assumptions, right? So what are those assumptions? First assumption is the material of the cylinder is homogeneous and isotropic. The material of the cylinder, that is homogeneous and isotropic. What do you mean by homogeneous? Homogeneous means the material composition is same throughout. It means the material used for the manufacturing of that cylindrical cell. So the arrangement of the molecules in that material is same throughout. So if it is the same throughout, then that we call it as homogeneous, right? But remember, and isotropic, he is saying isotropic. Isotropic means all the properties of the material is same in all the direction. If the properties of the materials are same in all directions, then such material we call the isotropic material. So this is the first assumption. We are making the first assumption as the material of the cylinder is homogeneous and isotropic. This is assumption. ಅನ್ಕೋತೀವಿ ನಾವು ಏನು ಅನ್ಕೋತೀವಿ, ದ ಮಟೀರಿಯಲ್ ಅಂತಕ್ಕಂಥದ್ದು ಕಾಂಪೋಸಿಷನ್ ಅನ್ನು ನಾವು ಏನು ಯೂಸ್ ಮಾಡಿರ್ತೀವಿ ಆ ಮಟೀರಿಯಲ್ ಅನ್ನು ಮಾಡಲಿಕ್ಕೆ, ಅದು ಥ್ರೂಔಟ್ ಎಲ್ಲ ಕಡೆನೂ ಆ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಸೇಮ್ ಇರ್ತಾವು, ಸೇಮ್ ಅರೇಂಜ್ಮೆಂಟ್ ಆಗಿರ್ತಾವು ಅಂತ ಅನ್ಕೋತೀವಿ. ಎರಡನೇದು ಏನಪ್ಪಾ ಅಂತಂದ್ರೆ ದ ಪ್ರಾಪರ್ಟೀಸ್ ಆಫ್ ದಟ್ ಮಟೀರಿಯಲ್ is also same in all the directions. ಯಾವುದೇ ಡೈರೆಕ್ಷನ್ ಅಂತ ತಗೊಳ್ರಿ ನೀವು, x direction, y, z or any directions if you take, the properties remains the same. ಸೊ ಅವಾಗ ನಾವು ಅದಕ್ಕೆ ಏನ್ ಕರಿತೀವಿ, ಐಸೋಟ್ರೋಪಿಕ್ ಅಂತ ಕರಿತೀವಿ. ಸೊ ಫಸ್ಟ್ ಅಸಂಪ್ಷನ್ ಏನು ಅನ್ಕೋತೀವಿ ನಾವು, ಆ ಸೆಲ್ ಅನ್ನ, ಸಿಲಿಂಡ್ರಿಕಲ್ ಸೆಲ್ ಅನ್ನ ಮಾಡ್ಲಿಕ್ಕೆ ಏನು ಮಟೀರಿಯಲ್ ಅನ್ನ ಉಪಯೋಗ ಮಾಡ್ತಾ ಇದ್ದೀವೋ ಅದು ಹೋಮೋಜಿನಿಯಸ್ ಇದೆ ಮತ್ತು ಅದು ಐಸೋಟ್ರೋಪಿಕ್ ಇದೆ ಅಂತ ಅನ್ಕೋತೀವಿ. ಬಟ್ ಪ್ರಾಕ್ಟಿಕಲಿ ಇಟ್ ಈಸ್ ನಾಟ್. ಪ್ರಾಕ್ಟಿಕಲಿ ಆಗಿ ಹೋದಾಗ ಅದು ಇರ್ಲಿಕ್ಕಿಲ್ಲ. ಬಹಳ ಅಂದ್ರೆ ಒಂದು ಫೀಟ್ ಮಟೀರಿಯಲ್ ಸೇಮ್ ಇರುತ್ತೆ, ಅದಾದ್ಮೇಲೆ ಸ್ವಲ್ಪ ಎಲ್ಲಾದ್ರೂ ಒಂದು ಮಾಲಿಕ್ಯೂಲ್ ಮಿಸ್ ಗ್ಯಾಪ್ ಆಗಿರುತ್ತೆ, ಏನೋ ಒಂದು ಹೋಲ್ ಇರುತ್ತೆ, ಸೊ ಅರೇಂಜ್ಮೆಂಟ್ ಆಫ್ ಮಾಲಿಕ್ಯೂಲ್ ಸಮಥಿಂಗ್ ಎಲ್ಸ್. ಬಟ್ ಫಾರ್ ಅವರ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡಿಂಗ್ ಟು ಡೂ ಫರ್ದರ್ analysis in this thin cylindrical cell for your diploma stage, so this assumption is necessary. So we are making that the material of the cylinder is homogeneous and isotropic. The cylinder is considered to be thin-walled. So next assumption is the cylindrical is considered to be thin-walled. The name itself is the thin cylindrical shell. So the wall is made up of very small thickness. The walls of that cylinder is very thin. That is the second assumption. Third one is the stresses are uniformly distributed. The stresses, because whatever the liquid or a gases you are going to store inside the cylindrical cell under pressure, because of that pressure puts the force on the walls of that container. Because of that force, there are some stresses are induced in the cylindrical shell. So what are the stresses are induced? Those stresses are uniformly distributed. This is one more assumption, but practically it is not correct. It may not be correct practically, but for our further calculations and all, we need to assume this is one more, that is the stresses are uniformly distributed. Then radial stress are neglected. So radial stresses are neglected in this case. That's the fourth assumption. And this one, to make it as fifth assumption, is number 4. This fifth assumption is the plane section remains plane before and after the application of internal pressure. So the structure of that the shell before in plane iruto, even after applications of the internal pressure also, that remains plane. So that remains plane. So that is one more assumption, right? So after applications of the internal pressure, the suction may change, but the assumption is that we are assuming even after applications of the internal pressure also, so that it remains the plane only. Then now we'll see what are the failure of thin cylindrical cells. So now yavaga thin cell alli ನಾವೇನ್ ಮಾಡ್ತೀವಿ, ಗ್ಯಾಸ್ ಆಗಲಿ ಅಥವಾ ಲಿಕ್ವಿಡ್ ಆಗಲಿ ಅಂಡರ್ ಪ್ರೆಷರ್ ನಾವು ಸ್ಟೋರ್ ಮಾಡಿದಾಗ there are chances of bursting. There are chances of breaking of that cylindrical cell takes place. So how it fractures, how it is going to break, because of what stresses, because of what forces the failure takes place. So all these we can study in the failure of thin cylindrical shell. when a thin-walled cylinder is subjected to internal pressure, the following stresses will be set up in the cylinder material. Namely, first one is circumferential or hoop stress. Second one is longitudinal stress. First one we'll see what is circumferential or hoop stress. The circumferential stress we'll see now. What do you mean by the circumferential or hoop stress? So as I shown in the diagram, see, look at this diagram. So this is longitudinal. In the second diagram, what I am showing, this is a longitudinal diagram. So this is like this, cell like this, like this. So when you are storing here something like this, when you store here, then definitely what happens, this cell, the stored air, or you can say the liquid under pressure, it puts the pressure on walls of this container. It will put the pressure on walls of the container in all the directions. Ella directionally ee pressure na ee wall mele hakutte. It will put the pressure everywhere it will put the pressure like this, right? Ee tara haakbekadaga heng fail agutte. So it will fail into two ways. So one, it may fail like this. One, it may fail something like this, or one, it may fail in this way, in this direction, like this, in this direction, right? So one in this way and one in this way. So it will fail something like this. So first one we'll see is circumferential or hoop stress. Circumferential means the total pressure along the diameter of the cell. How much pressure is putting on the diameter of the cell, along the diameter. See, in the second figure I am showing the pressure along the diameter means it is along the diameter like this, in the diameter like this. The pressure is put along the diameter like this. The pressure is something like this now, right? If the pressure is putting like this, means it is along the diameter, or I can say it is the circumferential, along the circumference, right? It is something like this. So the total pressure along the diameter of the cell now. How to find out the total pressure along the diameter of the cell? How are we going to put along the diameter of the cell now? So ಇದು ಯಾವಾಗ ಈ ರೀತಿ ಹಾಕುತ್ತೋ ಅವಾಗ ಏನಾಗುತ್ತಂದ್ರೆ ಇಟ್ ಮೇ ಫೇಲ್ ಸಮಥಿಂಗ್ ಲೈಕ್ ದಿಸ್. ಈ ತರ ಫೇಲ್ ಆಗುತ್ತೆ. ಯಾಕೆ? ಡಯಾಮೀಟರ್ ಅಲ್ಲಿ ಫೋರ್ಸ್ ಹಾಕಿದಾಗ ಸಮಥಿಂಗ್ ಲೈಕ್ ದಿಸ್. It is putting the force like this. ಈ ತರ ಫೋರ್ಸ್ ಹಾಕ್ತಾ ಇರುತ್ತೆ ವಾಲ್ ಮೇಲೆ ಅಂದ್ರೆ, ಸೊ ಇಟ್ ಮೇ ಫೇಲ್ ಲೈಕ್ ದಿಸ್. ಈ ತರ ಫೇಲ್ ಆಗುತ್ತೆ. ಸೊ ಈ ತರ ಫೇಲ್ ಆಗೋದ್ರಿಂದ now what happens, as I said, this is a thin cylindrical cell, something like this. It is having some thickness like this. It is having some thickness like this. It is thickness like this, right? So ಈ ತರ thickness ಇರೋದ್ರಿಂದ this is a T. This thickness is T. Here also the thickness is T, something like this, T, right? The intensity of pressure into area. Intensity of pressure means whatever the liquid or air under pressure you are storing there, so that is having the intensity of pressure P. That is having the pressure P. And the area, how to find out the area now? Area is the diameter into L. Diameter into L. Diameter into L means what he is saying, the projected area. Projected area means this area. This area. It is along like this. ಈ ತರ ಇರುತ್ತೆ ಅದು. ಕಂಪ್ಲೀಟ್ ಆಗಿ ಇರೋದ್ರಿಂದ ಹಿಂಗೆ ಕಂಪ್ಲೀಟ್ ಆಗಿ ಇರೋದ್ರಿಂದ, so this area you need to find out. This area. This area means the pressure is putting on this area. So because this is D is there, this is D and this is L. This is L. So D into L. So on this projected area, the pressure is putting. So the pressure is applying on this projected area. That is nothing but that is P into L. So I am taking here P into L. This is area. This is projected area. P is the intensity of pressure stored in that cylindrical cell, right? So now we can see how much resisting force is developed inside. So what is the area resisting this internal pressure? So ಯಾವ್ದು area this internal pressure na resist ಮಾಡುತ್ತೆ? So it means what is the cross section I have shown it here. E thickness ಇಲ್ಲಿ ತೋರಿಸ್ತಾ ಇದೀನಲ್ಲ, up to here this is the thickness will be there, something like this. There's the thickness. So this is T, this is T, this is T, this is L, right? So similarly here this is T. There are two sections, one on this side and one on this side. There are two sections. So what is the area of this? This is L into T. This side also L into T. Means it is 2 times of T into L. ಅಂದ್ರೆ ಈ ಏರಿಯಾ ಕಟ್ ಆಯ್ತು ಅಂದ್ರೆ ಇದು ಏನಾಗುತ್ತೆ, ಸಿಲಿಂಡ್ರಿಕಲ್ ಸೆಲ್ ಫೇಲ್ ಆಗುತ್ತೆ. ಅವಾಗ a thin cylindrical cell fails when these two areas will cut. ಯಾವಾಗ ಈ ಏರಿಯಾ ಎರಡು ಕಟ್ ಆಗುತ್ತೋ ಅವಾಗ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ this is going to fail. ಇವು ಎರಡು ಏರಿಯಾ ಯಾವಾಗ ಕಟ್ ಆಗುತ್ತೆ ಅಂದ್ರೆ when the internal pressure is applied circumferentially along the circumference. When this internal pressure pushes, then only it will fail along these two the areas. So now we can find out the resisting section. Resisting section means this is a T into L one side, T into L one more side, so it is become 2T into L. This is the resisting area. Resisting area means ಅದು ರೆಸಿಸ್ಟ್ ಮಾಡುತ್ತಾ, ಫೇಲ್ ಆಗಕ್ಕೆ ಬಿಡೋದಿಲ್ಲ, ಅದು ರೆಸಿಸ್ಟ್ ಮಾಡ್ತಾ ಇರುತ್ತೆ. ಎರಡೂ ಕಡೆ ಏರಿಯಾ ಫೇಲ್ ಆದರೆ ಮಾತ್ರ ಆ ಸಿಲಿಂಡ್ರಿಕಲ್ ಸೆಲ್ ಫೇಲ್ ಆಗುತ್ತೆ. So now next one is the circumferential stress sigma C is equal to total pressure divided by resisting section. The total pressure you have found out P into dl divided by 2T into L. So L and L gets cancelled, so this becomes PD by 2T. This is the formula to find out the circumferential stress. Circumferential stress is given by PD by 2T, right? And if neta L, this is the efficiency of the longitudinal riveted joints of the cell, then the circumferential stress is given by, so that is PD by 2T and longitudinal efficiency. So it means that now initially this is a one cylinder, something like this, right? So this is closed with a cap on both the sides, something like this. It is closed on the cap and this is riveted. These are lines what I am showing, these are rivet lines. These are rivet lines like this, rivet. ಫಸ್ಟ್ ಒಂದು ಸಿಲಿಂಡರ್ ಮಾಡಿ ಅದನ್ನ ಎರಡು ಕಡೆ ಕ್ಯಾಪ್ ಇಂದ ಕ್ಲೋಸ್ ಮಾಡ್ತೀರಿ. ಕ್ಲೋಸ್ ಮಾಡಿದಾಗ ದಿಸ್ ಕಾಲ್ಡ್ ಇಟ್ ಆಸ್ ದ ಸಿಲಿಂಡ್ರಿಕಲ್ ಸೆಲ್ ಅಂತ ಕರಿತೀವಿ ನಾವು. ಅವಾಗ ದಿಸ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಸಿಲಿಂಡ್ರಿಕಲ್ ಸೆಲ್, right? So if you call this as a cylindrical cell, then next when the internal pressure applies here, this internal pressure is along longitudinal. ಇದೇನ್ ಆಕ್ಸಸ್ ಇರುತ್ತೋ ರಿವೆಟ್, ಆ ರಿವೆಟ್ ಆಕ್ಸಸ್ ಮುಖಾಂತರ ಇಂಟರ್ನಲ್ ಪ್ರೆಷರ್ ಆಕ್ಟ್ ಆಗ್ತಾ ಇರುತ್ತೆ. So the efficiency of this riveted joint we consider it as this neta L. This is efficiency of the riveted joint. So when there is a circumferential stress comes, then there is a longitudinal efficiency comes. So you have to consider when efficiency of the rivets are given in the problem, then you have to take it as neta L. That's the efficiency of the longitudinal stress you need to consider. So the circumferential stress is PD by 2T. Longitudinal, remember of course here it is sigma C, circumferential is there, but here you have to take it longitudinal, opposite. If it is circumferential, the longitudinal rivet efficiency is considered at the bottom. So this is because I have explained here in this figure. So when the internal pressure P, so it is acting along circumferential, but for the rivet it is acting along longitudinal, right? So because of that you have to consider the longitudinal efficiency. So this is called as the circumferential stress, and this circumferential stress is also called as hoop stress. Remember, this is also called as hoop stress. Hoop stress. So the circumferential stress or hoop stress, both are the same. The second one is longitudinal stress. Longitudinal stress sigma 1. So consider the cylinder as shown in the figure. It is something like this. So when it fails along the circumference, so it is called as circumferential stress. If it fails along the longitudinal way, so then this is called as the longitudinal stress. So this is also due to internal pressure, and the same way I am going to calculate now intensity of pressure into area. Intensity of pressure is P again here, but the area is pi by 4 into d square. The area is pi by 4 into d square here now. So pi by 4 into d square is the area in case of longitudinal stress now. See, it is P into pi by 4 d square. So area of the resisting section now. What is the area of resisting section? So the area of resisting section is it is the dt. This is called as dt now. Area of resisting section is dt. So why this is called as a dt? Because it is going to fail in the longitudinal direction. So you are considering it as P into dt. So substitute the longitudinal stress, that is total pressure, by resisting section. So that is P into pi d square by 4 pi dt. Right? It is pi. So there is a pi dt, not dt, it is pi dt. So pi dt. So that is the resisting area section, that is, right? Resisting area section. So now why it is pi dt? Because it is something like this. So it is like this, something like this. So when it is going to fail this, ಯಾವಾಗ ಇದು ಫೇಲ್ ಆಗುತ್ತೋ, ಇದು ಫೇಲ್ ಆಯ್ತಂದ್ರೆ, so it is going to break into two holes. ಈ ತರ ಎರಡು holes ಆಗಿ ಕಟ್ ಆಗುತ್ತೆ. If it is complete one shell, ಒಂದು cylindrical cell ಇತ್ತಂದ್ರೆ, ಇದು ಮಧ್ಯದಲ್ಲಿ ಫೇಲ್ ಆಯ್ತಂದ್ರೆ, so it is acting longitudinal, means ಈ ತರ ಪ್ರೆಷರ್ ಈ ತರ ಆಕ್ಟ್ ಆಗ್ತಾ ಇರುತ್ತೆ ಇಲ್ಲಿ ಇನ್ಸೈಡ್, ನಾಟ್ ಹಿಯರ್, ಇನ್ಸೈಡ್ ಇಲ್ಲಿ. ಸೊ ಇಟ್ ಈಸ್ ಸಮಥಿಂಗ್ ಲೈಕ್ ದಿಸ್ ಅಂಡ್ ಅಗೇನ್ ಸಮಥಿಂಗ್ ಲೈಕ್ ದಿಸ್, ಈ ತರ. ಸೊ ಈ ತರ ಆಕ್ಟ್ ಆಗ್ತಾ ಇರುತ್ತೆ. ಈ ತರ ಆಕ್ಟ್ ಆಗೋದ್ರಿಂದ ಏನಾಗುತ್ತೆ, ಸೊ ಇಟ್ ವಿಲ್ ಬ್ರೇಕ್ ಸಮಥಿಂಗ್ ಲೈಕ್ ದಿಸ್ ಮೀನ್ಸ್ ಇಟ್ ಈಸ್ ಒನ್ ಪಾರ್ಟ್ ಲೈಕ್ ದಿಸ್, there is one more part something like this. This is a cell, ಈ ತರ. ಸೊ ಎರಡು ಪಾರ್ಟ್ ಆಗಿ ಬ್ರೇಕ್ ಆಗ್ಬಿಡುತ್ತೆ. ಸೊ ದಿಸ್ ಇಸ್ ಆಲ್ಸೋ ಲೈಕ್ ದಿಸ್ ಶೆಲ್. ಮಧ್ಯದಲ್ಲಿ ಕಟ್ ಆಗುತ್ತೆ, ಮಧ್ಯದಲ್ಲಿ ಕಟ್ ಆಗ್ಬಿಡುತ್ತೆ. ಸೊ ಮಧ್ಯದಲ್ಲಿ ಕಟ್ ಆತಂದ್ರೆ ಯಾವ ಏರಿಯಾ ಕಟ್ ಆಗುತ್ತೆ, ಈ ಏರಿಯಾ ಕಟ್ ಆಗುತ್ತೆ. ಸೊ ಈ ಏರಿಯಾದ ಏನ್ ಬೇಕು ನಿಮಗೆ, ಫಾರ್ ದಿಸ್ ಏರಿಯಾ ಯು ನೀಡ್ ದಿ resisting. This is called a resisting area. This resisting area you need to find out. This is pi d, the circumference. First you have to take the circumference and thickness. Circumference and thickness. Thickness is t and circumference is pi d. Pi d is the circumference into t. So into t. So this is what pi d into t is the resisting area. So this area is resisting for failure because of the internal pressure in the e area ಏನಾಗ್ತಾ ಇದೆ ಅಂತಂದ್ರೆ, this area is resisting the failure. So that you have to consider it. So I am considering p into pi d square, p into pi d square by 4 divided by pi dt. This is a resisting force. You can take. This is a resisting force. And this is also the resisting force. It is not section. Resisting force. So resisting force is that, not area. The resisting force is equal to p into pi dt. So when you take, this is the longitudinal stress is total pressure by resisting force, that is p into pi d square by 4 into pi dt. So that is pd by 4t. This also tensile stress across the YY, and it may be noted that longitudinal stress is half of the circumferential stress. Circumferential stress is ಎಷ್ಟಿತ್ತು, PD by 2T ಇತ್ತು, ಇದು PD by 4T ಬರತೈತಿ. So if it is PD by 4T, then what happens, PD by 4T means, so it is a 2 times more. So it is half ಆಗುತ್ತೆ. PD by 2T ಬದಲಾಗಿ PD by 4T ಬರತ್ತಂದ್ರೆ, so this is half of that, right? So now this is, if you consider area of a cross section only, if you take this is the resisting cross section, then you cancel p here, you can take only pi dt. That's correct, you can take only pi dt, right? So pi dt, so then this is also, it is correct, it is resisting section only. If you take resisting total pressure by resisting section, the total pressure is p into pi d square by 4, resisting section is pi dt, right? So here pi and pi gets cancels, d and 1d gets cancelled, so it is pd by 4t. This is correct. Area of the resisting section is correct. That is you only cancel p here, you can take pi dt. That's all, right? So then next, similarly in the previous case we have seen what is circumferential stress. In the case of circumferential stress, we have considered neta L as a longitudinal efficiency, but in the case of longitudinal stress we have considered neta C, that is circumferential efficiency. What do you mean by circumferential efficiency? Circumferential efficiency means along the radial lines, along the circumference, the rivets will going to fail. So in the longitudinal stress, you have to consider the circumferential efficiency of the rivets. But in the case of a circumferential stress, you have to consider the longitudinal efficiency of the rivets. So if you consider this, the circumferential efficiency of the rivets, then the longitudinal stress is given by sigma L is equal to PD by 2T and epsilon C. This is one. This is not, I think, 2T epsilon C. It is 4T. Sorry, it is 4T. You can consider it as 4T epsilon C. 4T epsilon C. It is 4T epsilon C. Right? So this is the one. This is the longitudinal stress PD by 4T and C longitudinal efficiency whenever we are considering the circumferential efficiency of the rivets. This is the one. So thank you. This is the end of this session.